Welcome to the problem-solving set for the structure of DNA. Question 1. If bacterial DNA has 35% adenine or A bases, give the percentage of the other three bases, cytosine C, thymine T, and guanine G. To answer this question, we have to remember Chargaff's rules. Now he said because A and T base pair with each other, that the number of A bases has to equal the number of T bases. And because C and G base with each other, the number of G bases has to equal the number of C bases. Now remember that adenine and guanine are both purines, which means they have two rings. So these are purines. And thymine and cytosine are both pyrimidines, which means they only have one ring. So another way to say Chargaff's rules is that the number of purines equals the number of pyrimidines. And what that really means is A plus G equals T plus C. Okay, so this problem tells us that there's 35% A bases. So using this rule here, we know that A and T have to equal each other, so therefore there's also 35% thymine bases. Now this totals 70%, which means out of 100, there's only 30% left. Now because G and C have to be equal to each other, what we're going to do is divide 30 by 2, and therefore we get that G equals 15% and C equals 15%. And then if you add these together, for A plus G, you see that 35 plus 15 is equal to T plus C, which is another 35 plus 15. So these are the total percentages of all four bases in the DNA of this bacteria. Problem 2. In regard to double-stranded DNA, determine if the following are true or false. So double-stranded DNA obey Chargaff's rules, so let's write those just to refresh our memory. Chargaff's rules say that because A and T pair with each other, the number of A bases has to equal the number of T bases, and because G and C bind with each other, the number of G bases has to equal the number of C bases. Now another way to write this is that the purines, which are A and G, equal the number of pyrimidines, which are T and C. Okay, so let's go through these. For A, it says that the number of A equals the number of G. Now this isn't true. As you can see over here, the number of A equals the number of T. So this is false most of the time. However, can you think of any time where the number of A is going to be equal to the number of G? Well, this would only happen if all four bases are represented the same number in a double-stranded DNA section. So this is false unless they are both equal 25%. Because if one base is 25% and G is 25%, that means that all four bases must be 25% in a double-stranded DNA. Okay. For B, A equals C. Again, this is false unless all four bases are represented 25% of the time. Okay, C. C says T plus G equals C plus A. Well, remember that A and T are equal to each other, and G and C are equal to each other. So here, this purines equal pyrimidine, we're saying that A plus G equals T plus C. However, T plus G equals C plus A is also true. And for C, let's just do a little example. If A is equal to 30%, that means that T is equal to 30%, which totals 60%. Now there's 40% left, divided by 2, means that G equals 20, and C equals 20. Okay, so it's saying T plus G, which would be 50%, equals C plus A, which would be 50%. So C is true. Now let's look at D, and we can use this same example for D as well. T plus C here would be 50% equals G plus A is another 50%. So this is true, and this is the normal purines equals pyrimidines, because T and C are pyrimidines and G and A are purines. For E, T plus A equals G plus C. Again, let's use this example. T plus A in this case would be 60%, and G plus C would only be 40%. So this is false. And again, the only time this would be true is if both, or actually all bases were there 25% of the time. Okay, now let's look at F. We're going to use the same example. So it says G divided by A is equal to T divided by C. So for this case, G divided by A would be 20 over 30 is equal to T divided by C, which would be 30 over 20. Now this, obviously, these don't equal each other, so F is false. Let's look at G using the same numbers. G divided by A is 20 over 30 equals C divided by T, which is 20 over 30. So this, G, is true. For H, it says A plus G divided by 5 equals 10. So let's use these numbers for example first. So here, A plus G is 50%, divided by 5 does equal 10. You do 50 divided by 5. Okay, so that's using that example. So maybe you'll say, maybe it's not true in all examples, so we can do another one. Let's say now that A equals, let's say 45%, which means that T also equals 45%. When you add these together, there's 90%, which means that G and C together equals the last 10%. So G equals 5%, and C equals 5%. Now if you do A plus G here, you still get 50, so divided by 5 is equal to 10. So this is true. And finally, let's look at I. It says A plus G over T equals 10. So let's use this second example. So A plus G over T equals 10. In this example, it would be 45% plus 5 over 45 equals 10. Now obviously this is less than 1, but even if it's less than 1, you're adding it to 45, these don't equal each other. So I is false. Okay, so this is just some simple practice so that you get used to Chargaff's rules, because on an exam, teachers may give, just the percentage of 1 out of the 4 bases and ask you to find all of them. So this is a good way to understand the rules. Problem 3. Given the following base percentages, determine if each DNA sample is single-stranded or double-stranded. Now for these, again, we're going to use Chargaff's rules, which, remember, are that the number of A bases equal the number of T bases, and the number of G bases equals the number of C bases. Now Chargaff's rules only apply to double-stranded DNA, and that's because they're based on complementation pairing. So in a double-stranded DNA, we know that base A pairs with base T, and that base G binds with base C, and that's the reason why you get equal amounts of both. So if the percentages in these parts abide by these rules, we can say that they're double-stranded DNA. But if they don't, if for some reason you have even just 100% G, you know that that must be a single-stranded DNA sample, because if it was double-stranded, then all of those G's would have to base pair with C's, so you would get 50-50. Okay, so let's look at A. A says that G is 35%, A and T are both 15, and C is 35%. So if you see here, G and C are equal, and A and T are equal. So this is going to be double-stranded DNA. For B, G and A now are 35%, whereas T and C are 15% each. Now because A and T don't equal each other, and neither do G and C, which are the base pairs, we know that this has to be single-stranded DNA, or ssDNA. For part C, it says A plus C equals 60%, whereas G plus T equals 40%. So we have to write down the other Chargaff's rules that we have. So we have that the purines equals the pyrimidines, which means that A plus G, equals T plus C. However, through simple algebra, if you subtract C from this side and add it to the other side, and then subtract G from this side and add it to the other side, you can see that A plus C is equal to T plus G. Okay, so now it's saying that A plus C here is 60%, whereas G plus C equals 40%. Now this doesn't abide by this rule that we just found out algebraically, which means that this DNA strand must be single-stranded. Okay? And this part D is saying A plus G equals 50%, where C plus T equals 50% as well. Now this is abiding by the simple purines equals pyrimidines rule here, which says that A plus G has to equal C plus T. So because it abides by this rule, we're going to say that this is a double-stranded DNA sample. Problem 4. Most cells contain double-stranded DNA, but certain viruses may contain single-stranded DNA. Giving the following DNA strand sequences, determine if they could be from these unusual virus cells. Okay, so remember that when we're looking for double-stranded DNA versus single-stranded DNA, we want to remember that Chargaff's rules are only obeyed in double-stranded DNA because of base pairing. So this is where the number of A's equals the number of T's, and the number of G's equals the number of C's. So let's look through and count the number of every base and see if these could be double-stranded or single-stranded. So for A, let's go through and count the number of G's. So we have 1 G, 2, 3. So we have 3 G's. Now how many C's? 1, 2, 3, 4, 5, 6. So again, we're seeing right away, we're seeing that 3 and 6 don't equal each other. So they're not really obeying Chargaff's rules, but let's go through and count the others just in case. So for T, we have 1, 2, 3, 4, 5 T's. And A, we have 1, 2, 3, 4, 5, 6. So again, A and T aren't matching with each other, which means that A must be from a single-stranded DNA, which means that, yes, it can be from these unusual virus cells. Okay, now let's do the same for B. We have 1, 2, 3, 4 G's. 1, 2, 3, 4 C's. 1, 2, 3, 4, 5, 6 T's. And 1, 2, 3, 4, 5, 6 A's. Okay, so in this case, we're seeing that the number of C's do equal the number of G's, and the number of A's to equal the number of T's. So it's obeying Chargaff's rule, which is going to make us guess that these are double-stranded DNA strands. So it's not from these unusual virus cells. For C, G, we have 1, 2, 3, 4, 5 G's. 1, 2, 3, 4, 5 C's. 1, 2, 3, 4, 5 T's. And finally 1, 2, 3, 4, 5 A's. Again, obeying Chargaff's rules, so we're going to guess that this is a double-stranded DNA. Now for the second part of the question, it says determine any relevant complementary strands for these sequences above. So obviously the double-stranded DNA, which are B and C, are the only ones that are going to have complementary strands. So let me erase this so that we can see. and let's write out the complementary strands. So I'm going to just give us some room here. And remember, for base pairing, that the A base pairs with base T, and the G base pairs with base C. And also remember that double-stranded DNA runs anti-parallel, so where 5' end on one strand is, it meets the 3' strand of the other, and vice versa. So let's do B. We're starting with 5', so on the complementary strand it's going to be 3'. And then just go through. So G is complementary base paired with C, so it's going to be C, C. T binds with A, C binds with G, then T, G, T, T, G, C, A, C, G, A, T, A, T, A, T, and then 5', which meets with 3'. So that is the complementary strand for the strand shown in B. For C, again, we're going to run through anti-parallel, so we're going to start with 3'. T binds with A, and A binds with T. C, C, G, 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 A, C, T, T, A, G, C, T, A, G, C, T, A. So that's how you do complementary base pairing for DNA. So just remember that A binds with T, and G binds with C, and that you're going to run anti-parallel. Okay, so this is pretty simple once you get the hang of it, and it could be a few easy points on an exam. Problem 5. Name the bonds indicated by the arrows in the following DNA model. Well, let's just determine what we're looking at. This white part here is a DNA backbone, and that is made up of the carbon sugar, which is deoxyribose, and the phosphate group. And these pegs in the middle, in the helix, those are the nitrogenous bases. So it's saying, what are the bonds in this DNA model? So the bond pointed here on the right, that is pointing to the DNA backbone. And what is the bond between a deoxyribose sugar and a phosphate group? Well, that is, if you remember from the theory video, is a phosphodiester bond. And that is a form of covalent bond. And on the left arrow, that's pointing to the middle of two bases that are base pairing with one another. Well, what is the base pairing really? That is a hydrogen bond. So remember that when A and T bond with each other, they have two hydrogen bonds between them. When G and C bond with each other, they have three hydrogen bonds between them. So these here are the H bonds. Okay? So these are the two type of bonds that keep the DNA double helix together and makes it a perfect genetic material.